Vamos lá, pessoal, começar. Queria apresentar para vocês agora Luiz Miras. Luiz veio de São Francisco, Califórnia. Depois de 3 vezes ou 4 no consulado brasileiro. Conhece todo mundo lá, né, por nome. E Luiz vai falar de análise de vulnerabilidades e engenharia reversa. Então, para aqueles que vieram para cá, para ver bits e bytes, hexadecimal, etc. e tal, essa é uma das palestras que você vai gostar. Então, sem maiores introduções, porque não precisa, Luiz Miras.
Obrigado, Luiz. Bom dia, meu nome é Luiz. Bem-vindo à minha palestra. Eu não falo muito bem português, mas eu entendo um pouco. But the presentation is going to be in English, so you're going to have to worry about me butchering Portuguese. So this presentation is looking at different vulnerabilities through reverse engineering. The reason I came up with this topic is a lot of times people ask me, how do I audit a binary using reverse engineering? And starting from scratch, without doing other types of learning assembly or reverse engineering other things, it's very hard to get to that level. So this talk brings together lots of different topics. Some of it is looking at different vulnerabilities that we found in the past that have advisories available, that have exploit code available, and we can analyze these and understand what is going on with the vulnerabilities in order to understand how to find new ones. So some of the things I'm going to cover, this is the agenda. I'm going to cover the different types of reversing within security. A little bit of a assembly refresher. You don't need to know assembly to understand the talk, but if you want to follow through, this is just gonna, if you know some assembly from previous things you've worked on, this will just refresh it a little. And if you don't, that's fine. I'm going to step through and explain what's going on at a higher level. Then we're going to look at some of these vulnerabilities. These are all public vulnerabilities that have advisories available. They usually exploit code as well. Then we're going to talk about the tools that I use, some of the plugins that are available that I find to be really useful for this type of work. And then talking about how to go from an advisory to trigger the vulnerability. So these are some of the general areas of reverse engineering within security. We have malware analysis if you work for, let's say, a virus vendor, an IDS vendor, and you want to, you need to see what the malware is doing, decode it, etc. Another thing is if you're doing exploit development. Let's say you're fuzzing something, or you're doing a source code audit, and in order to write the exploit, you're going to have to reverse the binary and see how everything's laid out. Patch analysis. The second Tuesday of every month, there's new Microsoft patches. And right when those hit, there's teams everywhere, whether they're commercial teams or they're private teams, and they start reverse engineering the patches to develop exploit code, whether it's to protect systems or to attack systems. But this is a common occurrence that happens all the time. And finally, what we want to do is be able to do binary auditing, looking for these same types of vulnerabilities. So malware. The goals of malware are to be difficult to remove and difficult to analyze. Usually, the author of the malware doesn't want anyone to reverse engineer it. So they're going to use hackers, different types of obfuscation, and they're going to actually attack the reverse engineering tools. There have been attacks against IDA Pro, which is the most popular disassembler, through different vulnerabilities. Ollie Debug has a vulnerability in the output debug string. There's a format string command. Within output debug string, it doesn't handle format strings properly, and you can take over the debugger through analysis. And this is being exploited within malware and within different packers. One of the most popular packers is called Armadillo, and Armadillo default uses this to try to defeat the debugger. We're not going to look at malware. We don't want to worry about decoding obfuscated code, looking at packers. That's a field unto itself. What I want to look at, what I think a lot of people want to look at, is how to audit these type of things, how to find vulnerabilities, how to exploit them. So all these things, exploit development, whether you're coming from fuzzing, source audit, black box, what have you, as well as patch analysis and binary auditing. These are all looking at vulnerabilities, but at different depths. Let's say for the first one, you don't have to reverse engineer that much. You probably know the function that is vulnerable, maybe know some of the code paths, and you're just trying to figure out the layout of the memory so you can exploit it properly. Patch analysis, you're comparing two different binaries. You have a basic idea of what has changed, and that level of assembly and reverse engineering is higher than the exploit development, but lower than complete binary auditing. Complete binary auditing, you're going to take apart the whole program. You're going to look at different paths from where user input comes in, whether it's over the network, whether it's command line or what have you, and trace that through and try to find somewhere there's a vulnerability. So this is just a little refresher on assembly. There's two different types when talking about x86 assembly, which is what pretty much everyone's using these days. There's the Intel format and the AT&T format. The only reason this matters is if you're doing any work with GCC, Linux, GDB, any of the BSDs, anything based on the GCC, GDB toolchain uses the AT&T format, which is a little bit different than the Intel format. If you're doing reverse engineering on Windows, you're using Item Pro, OllyDebug, WinDebug, any of the Windows-centric tools, you're going to use the Intel format. So the basic difference is in Intel, you're going to have an opcode followed by the destination, a comma, and a source. And what this is going to do is it's going to take the EAX register and put it into the ECX register. AT&T does the opposite. AT&T moves from left to right. So in this case, it would move ECX into EAX. Unless you're doing work with Linux, any of the Unixes, anything with the GCC toolchain, you don't have to worry about this. Most people that are reverse engineering for vulnerabilities are looking at the Windows platform because it's closed source, and you have to reverse engineer because there's no source code available. All the examples that I'm going to show are going to be in Intel. Registers are a very fast memory within the processor. Usually, the general registers are EAX, EBX, ECX, EDX. The stack, the ones that are used for the stack are EBP, ESP, and generally the memory reference are EDI and ESR. These are generalities. You can use any register for anything. If you write your own custom assembly, some compiler optimizations, if you don't have a frame pointer or certain options that you can set, won't necessarily use the stack registers as such or some of the memory ones. But this is the general rule. These are move instructions. The first one is going to move between a register and a register, so it moves ECX into EAX. The second example takes an immediate value, so it takes the actual value 0x10 and puts it into EAX. This one is going to take whatever is at this address and put that into the register. So this is going to read a pointer into EAX. Same thing can be done with a register. It'll read whatever value is at EBX go to that memory location, take the value out, and put it into EAX. You can also use offsets. So you have a base and then an offset from there, and that'll put it into EAX. The next thing we have to look at are comparisons. Comparisons are the basis of how program flow works. You're going to make some type of a comparison, and then it's going to make a decision. Let's say you say if something, and then you'll execute a block of code. So this is just the basic logic. So you can compare registers to registers. You can compare registers with immediate values, and this will set what is called an E flag. All you need to know about the E flags is branching instructions are going to look at the E flag for the result and base their decision on where to go from there. Arithmetic operations also affect the E flag register. So this is branching. Non-conditional branching means that there's no choice, it's just going to take the jump. This first instruction is going to jump to this memory location. This one jumps through, it takes the value from a register and it jumps to that address. And this is a call, like a system call. This is calling stir copy. Conditional means that it's going to base its decision, whether it's a jump or not, on one of the comparisons we did earlier. This J and E, that means jump if not equal. So if you compare two registers, if they're not equal, say you compare the value 5 and value 6, those are not equal, then it will jump to this location. It's an example. You can test every different, there's tons of different combinations. You don't have to know all this assembly. I don't know all the assembly instructions. I have a help file that has all the opcodes, and I just know the most common ones, and sometimes I look up the ones that I don't use very much. The bottom one means jump if above. So if there's a comparison and one is higher in value than the other one, then it's going to take the jump. So I picked 3 vulnerabilities to look at. The first one is a very famous one. It's the Microsoft Blaster one. That I believe that vulnerability caused Microsoft to change the way they handled vulnerabilities and really develop the MSRC program. Is that correct? So as the result of this vulnerability, I think this one is a good one to look at. It's pretty simple in how it works, and it was a very critical vulnerability at the time. The next vulnerability is a client-side attack against the Trillion, it's an IAM client. So I wanted to show one that was client-side. And the last one is an attack against the DHCP server that comes with VMware. This is a recent vulnerability. This came out last month. So this was discovered by a group in Poland called LSD. They found lots of vulnerabilities when they were active. They found this one, and I believe, rumor has it, later they went to go work for Microsoft. So a remote attacker can run arbitrary code system on any machine that's not firewalled. There's no authentication required. And this is what the vulnerability is. When you access something in Windows, you can do // machine name / resource. The machine name portion, there was a static size buffer on the stack, and the only way to stop writing into that buffer is it was looking for this slash. When it found this slash, it said, okay, the name is done, and we can move on. I'm going to show what this looks like in assembly. So I know this looks like a lot of code, I don't know if, is this too small? Do I need to make the font bigger? Can you guys see in the back? Make it bigger? Okay. I have two different versions here. One is 5.1, and I'm also using 5.0 because one of the plugins I use doesn't work with 5.1. Okay, so this vulnerability is basically a for loop. What happens is the setup is just putting the buffers into certain registers. This is checking if there's the backslash at the beginning, and that doesn't get run again. The core of it is this loop right here. So what is happening is this AX is getting the bytes from the AX, that buffer is reading this, the machine name. And it's writing it into the buffer here. It then is going to increment it twice because it's Unicode and it takes 2 characters per 2 bytes per character. This reads in the next value into the AX register, and here we see it compares it with the backslash. If it doesn't find one, it goes back to the body. So this keeps going continuously until it finds the backslash. After the loop is over, it's going to terminate the string, but what we see here on this simple little bit of assembly is the attack. Because there's nothing to stop. You can put as many bytes as you want before that backslash and overwrite as much memory as you need to. It's easier to see in the, right now we're not looking at where the buffer is. You have to look at the function that's calling it because the buffer gets passed in. So this is an argument to this. It's passing a pointer to the destination buffer. So this function doesn't even have the buffer. It's called somewhere above this. And if we see who calls this, here's the buffer that is being passed to the function we were just at. And we see that this is 32 bytes. So we have a 32-byte buffer, and we can put as much data as we need to, and that's the overflow. And all it is this loop right here. So if we're looking at this type of vulnerability, what we want to do is we look at the advisory, we look at the exploit code, and we start trying to trace how it goes through the program to figure this out. So now we can move on to, is there any questions about this vulnerability? So this is a similar type of vulnerability. It's also going to be an unbounded write to a static buffer. The vulnerability in this is the trilling IM client came with an RSS reader that ran inside of the IAM client. If you had a rogue, if you took over an HTTP server that was providing a feed, you did some kind of DNS spoofing, whatever way you got that client to connect to your server, you can run arbitrary code on the client. This is very similar to the bug that we saw above. It is also a buffer iteration bug. It's a type of loop that there's a certain condition to stop it. There's no size check. It's only looking for some type of exit condition without a size check. And this was found by one of my friends, Matt Hargett, through some software he wrote to automatically look for bugs and binaries. That's no longer available. It's no longer on the market. So this is, let me increase the font a little bit. This is similar to the previous vulnerability, is that it's a loop as well. One thing you'll notice is I have a plugin in this version of IDA that colorizes loops. So this knows that it's inside of a loop and it's going to change the color, which makes looking for these types of things a lot easier. It makes some mistakes, but it's very useful. So it knows here that it's within a loop. So let's see what's happening. There's a call to receive. Receive takes data off the network and puts it into a buffer. So this is how the call works, and these are the different arguments. So there's a buffer being passed to receive. The length is 1, and then there's some flags. So this reads 1 byte at a time. And then there's going to be some kind of test or exit condition. So this is the test. It's looking for 0x0a. 0x0a is a new line. So this keeps on reading data until it gets a new line. So if you're looking at HTTP or something, this is an HTTP, it's going to get the data until it gets the end of the line, and then it's going to process it. But the only way to stop it is this 0a, the new line. So this is going to keep on going forever until you send a new line. So in order to, this is the same case again, where the vulnerable function doesn't contain the buffer, but it's going to be passed a pointer. The vulnerable function, the buffer that is vulnerable to getting overwritten is coming from somewhere else. So this is where the buffer is. It's within the parent of that function. And I'm scrolling to the top of the function where all the stack variables are declared, and you can see what size it is and that it's on the stack. So here's the buffer. It has, it's set to a size of 400 hex. 400 hex, I believe, is 1,024 bytes. Before hitting the end of the stack, there's going to be 800 more. So there's, you have a 3K buffer. If you send more than 3K of data, you're going to overwrite the stack information, and you may overwrite other things that are used within these variables or these other buffers. But you have a complete overwrite of the stack. and there's nothing to stop how much data is coming across. So when you're looking at doing this type of thing, this is the cycle that you're going to do. You look at an advisory. The advisory, it depends who wrote it, how much information is available. Some people or some research teams, let's say EI, puts a lot of information in their advisory. They'll give you some assembly. They'll tell you the vulnerable function addresses, so you can start disassembling, and you have a good starting point. Let's say ISS. ISS gives you almost no information. They're not going to tell you, they usually don't tell you the function. It may tell you the type of vulnerability, if it's an integer overflow, or if it's a stack overflow, or the type. But no addresses, no functions. The next step is going to be patch analysis. For this, I'll do a demo of a tool by Saber Security. If Felix is here, or maybe he's not, I don't know, that's the company that he does his work for. The product is called Big Diff. It's very useful. And it's used, it's used pretty much exclusively to do this type of patch analysis. There's another tool by EI. They have a free tool that does some patch analysis, or some diff analysis, but it's not as good. After you do the patch analysis, you have to try to find where the vulnerability is. All the tools are going to tell you is that there's been certain changes between the old version and the new version. And then you have to analyze that code to determine where the actual vulnerability is. After that, you're going to have to trigger the vulnerability. Whether you get it to the vulnerable part of the code, you get a crash, but you're going to have to use runtime analysis. You're going to have a debugger, you're going to send data, you're going to see how it's changing and how to get to the vulnerable part of the code. So this is a pretty new vulnerability. This came out last month. There's the VMware DHCP server. It only works for NATed VMs. So if you're running the VMs within NAT behind the workstation or ESX or whatever version it is, there are these issues. If it's bridged, then it's not in the bridged DHCP. It's only in the NAT portion. So this was reported by ISS, I guess IBM now, and there's multiple remote code execution. There's some crashes, there's some integer overflow underflows, and most of them stack-based. So what I posted in the previous slide is pretty much what the advisory says. Is that there's no other real information of where the vulnerability is, so it's up to whoever is doing this type of work to figure it all out. So the advisory doesn't give you very much information. Like I said before, some research teams give you more, some give you less. It's up to the policy of the company that they work for, or if it's a private research team, it's whatever they want to do. There's really no standard on this. So you're going to need to disassemble the binaries and diff the patches. So I've already ran the tool, the plugin here. I'm using an old version of BinDiff because I haven't upgraded yet. So this is a one rep back from the current, which is why I'm using IDA 5.0 because it doesn't work properly in 5.1. But this is what it's going to give you. These are the tabs. And the left-hand side, let me expand these a little bit. These are the functions that have changed when it has yes on the left-hand side. So right now we see that there's 4 functions that have been changed. These are all names that I have given the functions. It doesn't come like this. Usually they look like this, some random, whatever the number is, where the function is. But so arg reply, read packet, validate packet, and some other function. So if you want to look at what has changed, you right click and do visual diff, which I have already loaded up. The yellow boxes mean that something has changed. So to start out, it looks like there's now some type of size check. It's looking at the size of the packet for an ARP. This is an ARP reply function, and it needs the packet needs to be at least 0x2a. The previous one, the vulnerable version, doesn't check sizes. And let me make the font bigger on all these as well. So here we see what we saw in the graph is the packet size is being passed in. There's a comparison. If it's below it, if it's less than that, it's going to send some kind of error message. So the first thing that we notice when we start doing these diffs is that there's a logging mechanism. Somehow there's a way that all these messages are being passed somewhere, and we want to take a look at those messages because it's going to help us do our analysis. So we look at what strings are there available. And we look for anything that looks like log. Oh, there's a log file. And what we're seeing here is we're seeing calls to the registry. So there's going to be a registry key somewhere that turns on the log file, and we should probably look at that log file when we start exercising the program to see what's being written there. It's going to give us extra information while we're actively sending data. I have set it to log to a certain function, and this is the file that it produces. So it's just a standard type of information, what type of request it is, if there's any errors, exit codes, etc. So I have put the vulnerable version onto my machine is currently running the vulnerable version. So I have a debugger here. I'm going to set breakpoints on the entry to that function. So our reply has a breakpoint. This is an image running in VMware. It's natted right now. And I'm using Scapy to send some types of packets, so I can hit the DHCP program and kind of see how the program flow works, what is causing the data flow and the program flow. This is the first thing I'm going to send. All it is a broadcast Ethernet frame, and the type is 0x806. That means it's an ARP. That's the ARP type. So hopefully it's going to hit our function. And we send it, and we see that we hit a breakpoint. I'm going to increase the font somewhat. So now we've entered the program. We're inside of this function. We can start stepping through and see where the program goes. It's going to do some calls, and there was a comparison against a 1 that is being read somewhere within the packet. And if it's 1, it's going to jump over, and if not, it's supposed to drop down. And we could just let that keep running, and we start checking to see this has been modified. So it's writing to the log. And then we can scroll down and see what type of information is being sent back and forth. And what we start doing is adjusting the data that we send in order to be able to change the program flow. And then we start figuring out where the vulnerable functions are. One of the functions that has been changed was the validate. And the function that calls this actually is there's a memory copy. So validate returns some results. This here is going to be a copy. One of the things in the advisory is that there was an integer underflow and an integer overflow. So this is something that we want to look at, because this copy is based on the value of ECX, which is coming from EDX, which has a math operation using EAX, which is the result from the validate packet. So if there's a way that we can get EAX to be greater than EDX, EDX is going to be a negative number, which is, when evaluated this way, is a very large positive number, and then we have a memory copy that's unbounded until we hit a fault and it goes off the page. So these are the types of things that we want to look for when we're doing this type of analysis. One, want to look for new size checks. Anytime there's some type of integer underflow or overflow, look for mathematical calculations or comparisons that confuse signed and unsigned type data. So ItemPro is the disassembler that pretty much everyone uses. And by itself, it's useful, but it's not as useful and powerful as it can be if you start using the plugins. I'm going to demonstrate some of the useful plugins. We saw the bin diff, which is used to do the diff between the binaries to figure out what's changed. The next one is a PDB loader by Determina. It's written by Alex Sutteroff. And let me show you what that does. PDBs are how the Microsoft compilers store symbols. So without symbols, you just have addresses, and there's no proper names. So I'm going to have a binary here. This is a small program. It has no symbols. The beginning of it is actually this here. Let me increase the font again. But this function is actually main, but it doesn't know it's main because there's no symbols loaded. This function is not identified. There's a string being passed, and it's not identified. So we load up the plugin. Let me put the symbol file in the same directory. These are all the symbols that are in the symbol file. It's going to have functions. Some of the import thugs. So we say OK, and it's going to apply all these. Now we have this called main. We have the call to printf, and various other local variables. Some symbols have local variables, some don't. The public symbols, like Microsoft has for all their products, which you get from the symbol server, that only has public symbols, so no source code, no local variables. If you compile your own code, you're going to have private symbols, so you have all that information. So now we'll take a look at some of the other plugins. One is IdaPython. IdaPython is really cool because it allows you to script within IDA. You'll be able to manipulate the database, look for things, you can look for certain patterns. I'm going to show an example with that in a second. And these are very useful plugins. One is a comment viewer. So this shows you all the comments. So you can start reverse engineering a file and leave little notes to yourself. So something I do is put like XXX in a little comment, like look at this further, or this calls this. And if you haven't looked at this for a while, you just look at the comment viewer and it's going to dump all of them, and then you can sort and start looking at everything that you've made notes for yourself. A lot of times you can't reverse engineer everything in a single session, so you're going to have to make notes to yourself to look at later. I showed the loop colorizer already. This is a very good plugin if you're looking for something that is doing any type of crypto. It's going to look for constants, S boxes, CRC tables, and automatically find them by going through the binary. This program, this DLL that I'm looking at is called debughelp.dll. It's what is used to load symbols, and this is going to have a couple of tables in it. So we run find_crypt. And we see it found two things. It found a CRC32 table, actually two CRC32 tables. And then we can see where's that being accessed. And if we look at the instructions, it's doing exclusive OR with this CRC32 table. So whatever is using this function is doing some type of CRC32 calculation. So I'm going to show This I can give this file out, so I can't increase the font right now. But what this does is, when you have C++, you're going to have a lot of indirect calls. So I wrote an IDle script that takes the debugger. It uses PyMay, PyDebug is the actual debugger. And what it does is it's going to set breakpoints on everything in the vtable. It then exercises the program. Anytime the vtable, any of the functions in the vtable get hit, it's going to make a cross-reference. So let me explain how this works. So this line right here is an indirect call. We don't know where it's calling. It's reading the EAX register, and there's an offset. So we don't know where that's going. It's going to make it harder to reverse engineer the program. So this is what a vtable looks like. All it is a table of pointers into this object, and these are the functions contained with it. So in the case of the indirect call, somehow the base of it is going to be loaded into a register, and then an offset from there is going to be called to execute it. So that's how it's indirect. So in order to run this script, you just highlight the vtable. So it's running right now. It went through the program. This is just a test program that I used to exercise a lot of the functionality of the DLL. So now when we look at these will have cross-references. So now there's a huge table of where all these are called from. So I can, I'm going to reload it without running the command. So we can see the difference. That's what it had before. So after you run it, it's going to go through and it creates all the cross-references for you. And once you create cross-references, you can look at reconstructing objects. Let's say if something is called only within its own vtable, then it's going to be a private method, because nothing from the outside is accessing it. So you can start reconstructing object models. If it's called only from the outside, then it's public. If it's only called from methods within other vtables, then it's protected and there's some type of inheritance. So you start running this through different vtables, and you can start seeing how the objects come together, and it gives you a higher level overview of how to reverse the C++ program. But the point here isn't so much what the script does, is that there's this plugin that allows you to do the scripting. You can look for patterns of things that you found vulnerable in other programs. You can apply that to other things you're disassembling, or you can look at other vulnerabilities and see how those problems affected the vulnerability and catch those. The debugger I was using is the immunity debugger. There's links at the end of the presentation with all the URLs, so you can download it. but it's based on OllyDebug. It also includes Python scripting, and most of the standard OllyDebug plugins work. This plugin is very good if you're doing things that are looking for a debugger. Let's say you're reverse engineering iTunes. iTunes, because of DRM, anything with DRM is going to try to look for a debugger because they don't want you to figure out how the DRM works and be able to remove protection from the MP3s. Or whatever Apple's proprietary protocol or program format is. And then a breakpoint manager is pretty useful as well. So if you're doing this type of work, what you want to do is you want to understand older vulnerabilities. You want to use the advisory, you want to use the patch and the exploit. And as you progress, you can remove certain steps. Let's say you look at the advisory, and then you reverse engineer the patch, and there's an exploit available, but don't look at it. Try to figure it out yourself, and if you need hints, then you can look at the exploit and work back from there. And like anything else, history is going to repeat itself. So if you understand how the vulnerabilities work in these public ones, then you can go and start looking at for your own vulnerabilities. Muito obrigado.
How long do you take from the patch to the proof of concept exploit?
The question was how long does it take from the patch to the proof of concept exploit code, and it really varies on the difficulty of the vulnerability. If it's new protocol that I don't know, it's going to take longer. If it's a new file format that I don't know, it's going to take a lot longer. But most patches get reversed within a few hours on the first day. That's how fast the teams are working right now. Some of them take longer, some might take a couple days depending on what it is, but on average it's going to be done in the first day or two. Any other questions? Go ahead. So the question was, there's a malware that I'm looking at that I'm not familiar with the terms of A2. But so it's looking at that we mean by the well, using at the best probably what a lot of the shop do is they have their own sandboxes. Some people have some software that's to run in their program kernel. There are some other defaults so that anytime it's loaded and get it. So people are running on kernel modifying QEMU or blocks or WIAM or something like that to be able to get a different level access to it. Any other questions? Go ahead. What was that again? So the question was that there's malware kits available to make your own malware construction kit.
Any script kit can do malware sources or can build their things based on this case. You know something about that?
I personally don't deal with malware a lot. I do more like security type research, not the malware part of it. So I don't know. All right, thank you.
Muito obrigado, Luiz Miras. A gente vai fazer mais uma palestra, aí a gente para para o almoço. O almoço vai ser servido, não precisa ir em lugar nenhum. E a gente vai fazer também o leilão do Hacker Foundation, enquanto vocês comem e gastam dinheiro.